Common sense. You won't need to worry about item 1 or 2. You're just going to concentrate on the table here. The first column is number of cents. In science, we've kind of trained you to see a data table and think trial 1, 2, and so on. This is actually, if you have an electronic balance, we would have you put 1 penny on, leave it there, record the mass, add the second penny, the mass of the 2 pennies, and so on. In all likelihood, you probably do not have an electronic balance handy, and so we'll cut right to the data table filled out by me for you. So you want to press pause at the next slide and copy down the data into your notes. There's the table. Press pause and make these measurement recordings. Now think about your favorite Dum Dum lollipop flavor. Perhaps you chose the mystery Dum Dum flavor. Have you ever wondered what the mystery flavor is? Well, the mystery flavor of Dum Dums, that's a new invention by me, Dum Dums, is a very cost-effective strategy in the factory. So let's say they're running perhaps cotton candy flavor through, and they're near the end of the run. Rather than shutting down the machine and cleaning out the residue in the machine and the pipes and so forth, what they'll do is they'll just start the next batch, the batch of, let's say pineapple flavor. And for a short period, there'll be a mix of cotton candy and pineapple. And when they start producing the all pineapple portion of the run, and they'll stop and make all of these in-betweens the mystery flavors. Hence, no 2 mystery flavors in different bags are likely going to be the same mystery flavor in all likelihood. So there you go. The Dum Dum mystery flavor is a cost savings idea. The reason I bring this up is because in 1982 we had the mystery flavor of pennies. 81 and before, primary ingredient for a large portion of the circulation was copper. And copper took a big increase in price in the late 70s, early 80s, and the U.S. Mint, where coins are made, produced, saw that it would cost more than 1 cent to produce 1 cent. Not economically sound at all. So they changed the mixture, changed the recipe, and went from mostly copper and a little zinc to mostly zinc and hardly any copper at all. Now the 81 and 3 is absolutely the set recipe. Our 82s are our mystery flavor that maybe they're not exactly spot on. So just to make sure we have accurate data that we've given you, we only do the 81 and befores and 83 and after. And think of 82 as mystery Dum Dum flavor. What you do next is make a graph right in this area with 0 to 40 grams on the y-axis and 0 to 10 pennies on the x-axis. Now I know you haven't gotten the mass of 10 pennies, you've only done 4, but please do label the graph according to here. And we're only going to be looking at the data for the 81 and before pennies. So pause the video to give yourself time to make that graph. Here's a graph I did using the Vernier software program, and the plot on the x-axis is 10 pennies up to 40 grams. From your graph over here, predict the mass of 10 pennies before 1981. What we've done previously, mostly in physics with graphs, is just looking at relationships. Take that data and recognize what type of relationship it is that we have. For example, with the strong arm of the law of data, playground physics, we wanted you to be able to recognize that acceleration is inversely proportional to mass, and that acceleration is directly proportional to force. And we wanted you to take those 2 data relationships you saw from the graph and combine that to form Newton's second law. Acceleration directly proportional to a whopping force and inversely proportional to the mass. Now, we definitely see a direct relationship here. Just like playground physics, you knew that before you started this, that if I double the amount of pennies, my mass will double and so forth. But I had you do that because I wanted you to see the power within graphs, not just to recognize relationships. So this area of the graph here is what we would call experimental data. You actually measured these values from the 1 to the 4 coins. So that was actually done by you. On your graph, take a straight edge, it can be another page from the study guide, and line that paper up with the direct relationship you have here. And better than I'll freehand here, you're going to take and make a line, wow, all the way to the edge. Be sure to use a straight edge. Sure, my stray mark is straight as can be. But extend that direct relationship off to the 10 mark. This wavy line here should be a straight line. That is known as the theoretical data. Now, in the world outside of science, the word theory has a very loose interpretation. My always example is, oh, I followed the recipe, so the cake in theory should have tasted great. That's absolutely not what we mean by theory in science. Theory is essentially, that's the way it is. So the theoretical data is just letting fellow scientists know that I did not physically measure this, but I have confirmed the relationship, a direct relationship, and a beautiful one-to-one relationship that I extend outward. Then what we're able to do is continue this perfect straight line over here, and we don't have a chance of making this straight. Wowzer. And using your straight edge, take from the 10 penny mark over to the edge, wherever it should hit. I'm going to clean this slide up here. So this portion is the experimental data. You've used a straight edge to finish off your graph all the way to the edge. Then you've used another straight edge to take you over here. I was able to take advantage of the software that I used to make this graph and just ask, okay, what is the value of the y-axis right here? And was nicely informed that for the number of 10 pennies, the mass would be 31 5/500 of a gram. And so you're going to do the same thing. Instead of button pressing on a computer, you draw the straight line and look to see what your graph tells you. And that's what you will put for number 5. This method of establishing known data relationships and then extending that known relationship is how we do things like count stars in our galaxy. We don't actually count every single star in the galaxy. We take a section that we know the dimensions of, count the stars in that area, and then expand that data out for the larger area. It's very similar to folks who enter the candy competitions. We are loving the straight lines off to the side tonight. So you got the candies inside the jar and you're guessing. You tend not to guess the entire side that you can see. You pick a small area, count the jelly beans maybe in there, and then extend that out for the larger size. So a lot of great uses, not just for winning competitions, but a lot of great uses in the world of science, where sometimes we wouldn't have enough raw material to be able to physically measure them. If I wanted to do the mass of 10 billion pennies, it's going to be a little difficult to put that on the balance. But I can establish the known experimental data to then get the theoretical data. So you've listed up here, you, from your graph, predict the mass of 10 pennies before 1981. Hopefully you caught that. Now describe another method for predicting the mass of the 10 pennies. This is the one that probably went through your mind when you were writing this chart and saying, boy, did they really in class have to put 1 penny and then a second and a third? Can't you just take the mass of 1 penny and multiply by however many pennies worth you want? Yeah, absolutely. You could take the mass, known mass of 1 and multiply by whatever number you're looking for. In this case, it just happens to be 10. Now, item 6, what is the actual mass of the 10 pennies? Well, we took 10 pennies here, all 81 and befores, and placed them on a balance, and the reading is 30 and 9/10. 30 and 9/10. And others in the class also on their balances showed 30 and 9/10 of a gram. What's the difference between your prediction and the measurement? Well, I had 31 grams on my graph. Let's see, was it 31? 31 and 5/100ths, and so I'd subtract 31 and 5/100ths, and from that I would subtract the 30 and 9/100ths. Now, don't worry about a negative value. We're not destroying the law of conservation of mass or matter. We're not losing matter. So use what we call that absolute magnitude, absolute value. Keep the answer to number 7 a positive value, and it's likely to be under a gram. 8. What major force is acting on the pennies? Well, of course, you're thinking, I'm certain, gravity. We're going to play some musical pages here. We will come back and finish this. And as you see down here, you're spying the word wait, which the title of the study guide is Wait for It. You finally in your physics career are going to be able to correctly use the term wait in your physics classes. So musical page 2-3, we have scales. And you should be able to answer A, B, and C. 3 parts to C, so press pause. The SI unit of mass is the kilogram. I don't know if I dare try. What is the SI unit of force? From previous study guide, that is the Newton. Or perhaps you wrote the definition of a Newton. It's the amount of force to move 1 kilogram through a distance of a meter at a rate of each and every second. The instrument used to measure mass, what we've been using for a couple days now, is a balance or balance scale. And for force, the SI unit is the SI instrument used to measure force is a spring scale. And the spring scales that we'll be using look very similar to this. And we have some spring scales that measure forces, and forces being a common example, pushes and pulls. We have some spring scales that will measure push force as well, where the top has a piece that extends out that you can push on. It pushes back on you, thanks to Newton's third law. We know about this with interactions. And it'll give you a reading in newtons of how much force. The more classic way of a spring scale, and of course that's why they're called spring scales, is to pull down on this hook, and the hook pulls up on you, and you're able to get a reading in newtons. So you'll be using spring scales in the lab to measure forces. And if you look at the springs, they're different sizes, different compression rates, and the different colors denote the maximum level of newtons that each can have. The lowest one usually goes to about 2.5 newtons. We have white ones that go to about 20 newtons. All right, we have mass, balance, or balance scale, force, spring scale. And this is why in Physics A we were so particular not to have you just say a scale is used to measure mass. We wanted to focus on the term balance or balance scale. All right, ultimate question here of brilliance for you. Inertia. What is inertia measured with? Well, mass is inertia, or inertia is mass, and the instrument used to measure mass is the balance, or the balance scale. So absolutely, inertia is used, balance is used to measure inertia. D. Weight is a specific type of force. A force, as I've mentioned, is a push or pull resulting from the interaction of objects. So here we go, my friends. A moment you didn't know you were waiting for is the definition of weight. An object's weight is the force resulting from Earth's gravitational field pulling you towards the center of the Earth. An object's weight is the force resulting from Earth's attraction, pulling you towards the center of the Earth, or you, or whatever the object is. An object's weight is the force resulting from Earth's attraction towards the center of the Earth with the object. We do more musical pages, the hurry up and wait page, and see how great your 15-second working memory is to jot down what is weight. And if you need to, you can confirm back to the scales page that weight is how much force the Earth is pulling objects towards Earth's center. Before we continue more on hurry up and wait page, scales, and common sense, let's just pause for a moment and reflect that absolutely mass and weight are two very different things. Now, in other science classes, like life science classes, botany, zoology, meteorology, you're not going to worry so much about mass and weight. And in biological speak, they'll be used interchangeably. In the world of physical science, sciences such as chemistry and physics is the two big ones. In physics, of course, we obsess about mass and weight being different because weight is a force, and forces are one of the major components of things that we study in physics. We study forces, fields, energy. So when it comes to mass and weight, we're very specific in their difference. Think about our last unit, dynamics, what causes motion, forces. So it's very important we separate the two. In the world of chemistry, they're not dealing so much with forces and what causes motion, and so they will tend to use mass and weight interchangeably, much to the chagrin of their cousins in physical science of physics. So physicists, absolutely crazy folks we are, and we do very much obsess that mass and weight are two different things and get furious when they're used interchangeably. So quick chart just to recognize and organize our thoughts. Loose definition, mass, it's the amount of matter, it's inertia, whereas weight, amount of force Earth pulls objects towards Earth's center. We use two very different instruments to find the value for mass versus weight. So two different quantities, two entirely different measuring tools. And similarly, two completely different units. Kilogram for mass, Newton for weight. So absolutely, mass and weight are two different things, and you need to be very conscientious in physics. Do you mean mass or do you mean weight?